Yes. So one of the problems that we have with remote virtual classrooms that I would like to improve better than previously posted is that we have this hackathon at the end, and the Xbox because basically
doesn't make so much. Oh, now I have my camera back. Okay, thank you. Good. Let me, change. And today is the important day for baseball. That's why we're there. My wife said today. Uh, it, I guess they will find out if they get to the next round. Oh yeah, it's huge. Yes, yeah, yeah. Uh, they lost to Australia, which is crazy. That's like losing Spain losing to Australia in soccer. That's fine. That would be unheard of. Right? I mean, uh, Australia actually they are as a whole nation they're very much into sport. So they do have things like that. Just baseball is not one of that. Okay. So Okay, let me get used to this. You never wear that. My voice will be out. Hello? Okay. So then we will be working together with students from Germany. Also, there may be some students from India joining us. That's not sure yet. And the first thing is the project that we want to work on, this hackathon. So our colleagues in Germany have this kind of robot. Actually, not. I thought that TurtleBot has Omni wheel. Or maybe that. Yeah, that doesn't really matter. But I think they have this kind of robot, except they have it with Omni wheel, so it can drive off in any direction with the counter wheels. Yeah, maybe there is an extra add-on or something. I'm pretty sure I saw them using it. I'm not such a big fan of buying these kind of robots. My research is in humanoid robots. We won't use it in the field very much. But I do like the possibility of building our own robots cheaply. And so what I have in mind is Jackie's version of the TurboBot, which is admittedly not looking so nice, but it gets the job done. And what we have is two RC servos and the motor controller is done by a Raspberry Pi Pico 2W or Pico 2. The W is the one with the Wi-Fi interface, so then you don't need to run it. And that one is about 300 MT. Much cheaper than the turbo one. Actually, let me see what turbo is. 600 euros. And so that's quite a bit more. The other thing is that we have now sort of described what the final project is going to be for the course, but I really think the most important part is not so much I don't think it's actually the project in itself. It's the chance to have to work together with a team of students from another country. Now, for the Taiwanese students, it's usually a bit more exciting to work with people from Europe. For you too, you're like out of sample, out of, and sample. But I hope you still have fun with it. So today I want to start having the first kind of small project. So we will just set up random groups and you can work together on just a 1 hour task, implementing a simulation of this particular side of the robot. Now, at the heart of the control here for this particular robot, if you have a look, then I got the wheels from 7-Eleven. I just asked them to give me the caps from the milk jugs. And so we get wheels that way, and this is the jar, the plastic thing at the right size. And as motors, we want to use these RC servos. Now, they are very cheap. They are extremely popular. They're used in all kinds of remote controlled airplanes, cars. They are all based on the same protocol. They're not really used for robotics. They have a lot of drawbacks compared to the motors that they have in the Turtlebot. In particular, they don't allow any feedback. Like they are, all you can do is you can send a position to it. So it's a servo motor. Okay, which means.
Okay, so is there a website?
Yeah. I didn't actually want the recording. I wanted a live feed.
Yeah.
Because I can record here. Actually, let me just start recording. No? Let's see if this works.
Hello? Well, how come this worked
Actually,
before? You have that on the whiteboard.
Oh, yeah.
I got the right.
It's sped up now from before it was 919, now it's 929. Okay.
There it says 20 frames per second. Liar.
It's quite a big delay. But
okay, so servo motor as opposed to a normal motor,
you have to put that on the YouTube. Actually, today's
servo motor usually means that you can set it to a particular angle. You want 10 degrees,
creation,
100 degrees,
and then screen,
and then the motor will go to that position and then stop.
Now he took my camera away.
So they use video.
So is there a webcam inside there?
Not the propeller, which is a continuous revolution. Servo motors usually can only rotate the
Anyway, we got a little bit of money, so we bought some camera.
Plus or minus 90 degrees.
Okay, connect this one. And then I have that. And we can see the whiteboard, okay, and
the other thing that for lots of so we use those in robotics, of course, all the time. If you want to build a robot arm, then you need to be able to move it.
This will be like in a TV studio,
right? Or the legs of a robot.
Yeah. Maybe in the back.
But we can trick the controller, which is what I want to do today. We can pull the hardware.
Well, it can't be worse than
the other thing for robotics,
which is one of the
intelligent robot servo motors.
And And that's
They have a
really
lot
just
of
that.
features
Just
nowadays.
like
Robotics, the company from Korea, was the one that sort of dominated the market.
No, I think they edited
20
like
years ago. Everybody was using their servo motors.
okay. I don't know. I just
But
read
now,
once
there's sort of a
with
new
it.
generation of
One of the top things. I didn't
electric
actually see it.
motors with the pancake
Supposedly that's what it is.
unit. And those are the ones that are used in the new
Maybe I'm being
they have much better power.
maybe I'm being unjust.
So it's a very interesting time
Artistic
because these new humanoid robots.
The picture that I
really
saw,
generation,
I did see a picture.
our power to weight ratio
that
is much
was
improved,
that.
which is why these robots now.
And I'm too scared
Before,
to go there now.
the gear reduction is
Because really
so high that there is no way that you'll be able to.
Oh, now I have my camera back. Okay.
Didn't have
Thanks.
Now we can. And these kind of motors, they allow you to read back the current position, they allow you to read back the current velocity of the motor, they allow you to read back the current torque, the temperature, they can set baud rates, you can send commands to a whole, one of the big things that they have is they have a bus architecture, so you connect your controller to motor 1, and then motor 2, motor 1 goes to motor 2, motor 2 goes to motor 3, motor 3. On the arm of a robot, you just have one wire basically going through.
Oh yeah, it's huge.
RC servos, we can't do that, they all need separate
They
control
lost
lines. So, for an arm,
like
if you want to build a robot arm with those, then
that's
you
like
have to
Spain
run
losing to Australia in soccer.
cables to the arm, like from here to the controller.
That would be
Elbow to
unheard of. I mean,
frontal plane to the controller, shoulder.
but really, actually, they are.
So just getting all the wires
They're very much
done
for.
used to be quite difficult for humans. Actually, it still is.
Baseball is not
Wiring
in their path.
With robots. Most of the time when our robots die, unexpectedly, because the wire has pulled out or sheared or something with a connector with So these RCs are also the new robotics modules. They are all controlled using either CAN bus or serial bus or RS-45, also the type of the serial bus. So you would send real packages like FF0329 and set the motor speed of motor with the IT03 to speed 20.
Hello? Okay.
But these RC servos are much simpler and they're controlled by what's called
We will
pulse modulation.
working together with students from Germany. Also, there may be some students from India.
And that control is
and
something like that.
the first thing is
Then it goes low.
that we
One
want to
wire.
work on, the Chaka
High, it goes low. And then goes up again. And the position of your servo is determined by
So our colleagues in Germany have this kind of
duration of this both phases.
They have it.
So that means this width
I thought that
was from
first
0.7 to 1.9, usually 10 milliseconds. So it depends on the specific company, the turbo motor.
Okay, that doesn't really matter.
The usual range. And
But
1.5
this kind of robot that they have is only wheels, so it can drive off in any direction. There is no wheels.
I think you can like change it and make it.
and you can stretch it out for some
Yeah, maybe
motors.
there's an extra add-on or something.
Others are cut out.
I'm pretty sure I researches in humanoid robots.
then it would be very short hauls.
I do like one side, the possibility of building our own robots.
And then if you wanted to send it
And
to the other
so what I
side,
have in mind is Jackie's version of the turtlebot,
you have to keep sending this.
which admittedly not looking so nice, but it gets the job done. And what we have is
It's
two
an absolute
RC servos and
If you send a pulse,
motor controller is done by
send a pulse,
Raspberry
that
Pi
is 1.5
Pico
milliseconds.
or the W is the one with the Wi-Fi interface, so then you don't need to run a cable, you can just send commands via Wi-Fi. And that
So,
one is about
internally-
100 TD, so it's much cheaper than
How that works is that we do have a motor.
actually, let me see what robotics is looking for.
That motor is set to a bunch of gears. Very primitive.
800
For
euros.
years, we actually bought the expensive,
Yeah.
more expensive RC servos with metal gears. The very cheap ones only have plastic gears.
So that's quite a bit more
Metal gears.
than I would want to spend.
And then here
on the,
is the output tab. So this is kind of what that looks like.
The
The
other
gear
thing
reduction depends on the kind of motor that you
is
buy.
that we have
The
now sort of described
higher
the
gear
project
reduction,
is going to be for the course,
the
but
lower
I
the
think
output,
the most important part
the
is
speed is
not so much,
but you will have more torque, because this torque is going to be transferred to the motor.
I don't think it's actually
The
the
lowering of
building
gear reduction is the faster
it's
you
a
go.
chance to have to work together with the team of students
Power
from other countries.
The less torque you have.
Now, for the Taiwanese students, it's really a bit more exciting.
What you're
To
controlling
work with people from
you're
Europe.
exactly.
For you too, you're like
These ones
out of
are
sample.
pretty good,
Out of
kind of like Swiss Army knives.
and
turbo.
sample.
They're right in the middle.
I hope you
Do a
still
pretty
have
good
fun.
job.
So today I want to start having the first kind of small project. So we will just
Now, how does the motor actually
and
stop?
you can work together on
How does it go to 10
on
degrees?
our task, implementing a simulation of this particular style of robot. Follow me back. Now,
The motor
at the
speeds,
heart
and then
of the control here for this particular robot,
has to stop.
then
But how does it
the
go?
wheels from 7-Eleven, I just asked them to give me the caps from the milk jugs. And so we get wheels that way, and this is the jar, just a plastic thing that I found at the right size. And as motors, we want to use these RC servos. Now,
Well, if it wants
they're
to
very
be-
cheap. They are
At 10 degrees, he has to know what the current
extremely popular. They're used in all kinds
There
of
needs to have some
airplane
feedback.
cars. They're all based on the same protocol. They're not really used for
From the
robots.
position
They
of
have a
the
lot of
output
draw
shaft.
compared to the motors that they
The
have in the turtlebot.
electronic cord.
In particular,
And the controller controls the motor.
they
But there has to be
don't allow
some feedback,
any
otherwise there's no way the motor could turn.
all you can do is you can send a position to it with the servo motor.
This feedback can be done in
Right?
several different ways. You may have heard of encoders, motor encoders. Those are basically like your optical mouse. Before the optical mouse, there was a little wheel with little slots, and it would turn, and then the light would shine through, and you could count the number of pulses.
Yeah.
That's an encoder. That one is very high accuracy, but the problem is it's only relative. It can only So then, with an encoder, you need to
How
have
come this
some kind of
before?
additional sensor that allows you to
On the whiteboard,
reset
I
it
got
so that you know when you hit zero. So then, that was done using end switches. So maybe you have a switch when the servo motor hits one end.
Yeah, it says 20 frames per second. Liar.
And then you switch and you could record on that.
Okay, so
And
servo motor
for a while.
as opposed to a normal motor.
And there won't be a problem. The problem is the end switches usually needed the most when you turn on the motor. When you
Servo
turn
motor
on,
usually means that you can set it to a particular angle, like you want 10 degrees.
after that, it worked
100 degrees.
But nowadays,
And then the motor will go to that position and then stop.
not used anymore.
They used to control ailerons.
RC servos use an absolute position controller,
Many years.
which is really just
Not the propeller, which is the continuous.
potentiometer, which is a
Servo motors usually can only rotate
circular resistor.
about
And then,
90
as the motor turns, there's a
plus or
little
minus
metal
90
path that
degrees
moves along.
range of.
And then you can measure the resistance of this resistor, that tells you then what the current is. And this is also, this is pretty standard technology, still used a lot today. The more modern style is
The other thing that for
magnetic
lots of, so we use those in robotics, of course, all the time. If you want to build a
more
robot
style,
arm,
and then there's a
then you need to be able to move
that is
it.
sensitive to the magnetic field.
Something like
Those are very
that.
nice.
Or the legs of the
They are
robot
very precise.
to walk.
They are absolute and they're very easy to put them on the output shaft.
We can trick the controller, which is what I want to do today.
You can do that on the output shaft or inside the servo motor.
We can pull the hardware.
happens.
Now, the other thing for robots is, intelligent robot servo motors, they have a lot of features nowadays. Robotics, the company from Korea, was the one that
Our problem with the
dominated the market for the
robot,
last
doing a
20
robot,
years or so.
you cannot use the motor directly. I cannot just.
Everybody was using
the
their
motor because.
servo motors. But now there's sort of a new generation of direct drive motors with the pancake gear reducer. And those are the ones that are used in the new humanoid robots, the Uni-3, the ones that can do backflips. They have much better
The
power.
motor spins about a couple of thousand
So
times.
it's a very interesting time
So,
because
there'll be many
these
groups,
robots is really a generation.
and, there's no
Power
way.
and weight ratio is so much.
If you had enough
Why
power,
these robots
these small motors, one that don't have enough
The
force
gear
to actually turn the,
there was no way
at that
to
velocity.
be able to jump.
But even if you have more power, and boom, the
Now,
thing will be way too fast. So we need to have the gearbox.
and these kind of motors, they allow you to read back the current position, they allow you to read back the current velocity of the motor, they allow you to read back the current torque, the temperature, they can
So-
set baud rates, you can send.
How do we do that?
A whole, one of the big things that they have is they have a bus architecture, so you connect
Have you
the
guys
controller
done
to motor 1, and then motor 2, motor 1
Yeah,
goes
yeah,
to
yeah.
motor 2 goes to motor 3, motor 3. On the arm of a robot, you just have one wire basically going through. Whereas with these RC servos, we can't do that, they all need.
But what happens
control
here
lines.
is-
So,
With this controller
for
board,
an arm,
for him to be
You want to do the
the
robot.
controller to move that.
then you have to run
That particular controller, in
a
this case, the
cable
PD
through the
controller.
arm, like from here to the controller.
Yeah,
from here to the
except no,
controller to the controller, frontal plane to the controller.
So have
back to
you-
the controller.
You guys
So
work-
just getting all the wires done, used to be quite difficult for humanoid robots. Actually, it still is. Wiring is a big problem. pull out or shear or something like that, or the connector with something.
One of the interesting things is that people
So
think
these RCs are also the new robotics modules. They're all controlled
because
using
let's say
CAN bus
at
or
10
serial
degrees,
bus
and I want to
or
move to
RC45
100
also.
then some kind of an algorithm you could come up
So
with.
you would
say, oh,
send real packages.
okay, if I'm at 10, I want to go to 100, and I want to move.
Set the motor speed of.
So I turn on the motor plus,
Yeah,
then this one here will move.
Speed.
Right, so it'll be 10, 11, 12, 13.
But
Then
these
I
RC
RC
servos
servos
are much simpler and they're controlled by what's called pulse modulation, PWM.
It's not quite that
And
simple.
that control
Even
is
a seemingly very
something like that.
control problem like that
There's a high phase,
requires a little bit more
low.
thought.
It's one wire.
The reason is
High
because
low,
when you wait
and
until
then
you're at 100 and then stop,
goes
and
up
the
again.
motor's going to keep
And
turning.
the position of your servo
It's going to stop at
is
105.
determined by
Then he said, now I'm at 105, but I want to go to 100, so I turn right.
the duration of
Then you
the
turn the motor on,
phase.
105, 104, 103, 102, 101, 102.
So that means
Now I stop. Oh, now I'm at 98. So your motor will never actually stay still exactly 100.
It depends, milliseconds.
As we'll see in the afternoon, not only will it
So it
oscillate in
depends
a very
on
rapid way.
the specific company, the specific.
So that's why
motor
there's
they
this
have,
control.
but that's the usual range. And 1.5
Tries
is usually
to get the motor to that position.
home
So what we want to do
position
is
1.5 milliseconds.
for this motor to turn continuously and to be able
And you can stretch it out for some of the turbo motors and
fast
turn them slightly
and medium
further.
speed and slow
Others
speed
are
forward and backwards and backwards.
So if you want to send,
And the way that we do that is, you gentlemen,
this command, then it
how do
will
we get
be
this motor
very
to
short
turn?
pulse, so it will be on one side of the turn. And then if you wanted to send it to the other side, this interval has to become,
I can't make it turn by going 1, 2, 3.
and you have to keep sending this
I
at
need that.
20 hertz
It only has plus or minus 90.
above that speed.
It changes from the current position, or it's an absolute?
It's an absolute value. Yeah.
Or independently of the position, when you send
Uh-huh.
that time, it will go to.
No way to do that.
If you send a pulse if you send a pulse that is 1.5 milliseconds, it will.
Then what do we discriminate?
It's not a relative control, it's an absolute.
Not the gears. We disengage the servo. But then
So
we
internally,
measure thing that says what position.
how that works is that we do have a motor,
And then we will set this
that motor is set
the
to
whole
a bunch
position
of
0
gears.
degrees.
Very
So then,
gears. We actually bought the extension ones, these are
Oh, I need to go to
metal gears, very cheap ones,
We'll
but
have
not
a lot of
plastic gears, but they're very,
power to make the motor turn
better to use metal.
into that direction.
And then
Now this connection here is up,
here
so
is the
the
output.
motor will just continue turning,
So this.
but the actual readback from the sensor is not going to change. So he's still going to read 0
And the
degrees.
gear reduction
So
depends
more
on
power.
power.
What can you keep? Which
The
means the motor will spin quickly.
higher
If you go to
gear reduction
10 degrees, then let's say, oh, I'm already at 0, so 10 degrees, I don't need so
lower
much power.
output
Slowly.
wheel is
So then it'll go
turn.
slowly. If
So
you
your
go to
speed
minus 10
is
degrees,
lower.
it'll turn backwards.
But you will have more torque because less torque is going to be transferred to the motor.
So we're kind of using,
The lower your gear reduction,
kind of
the
cheating
faster
the
your motor can move, but the less power, the less force, the less torque you have available. To actually turn things. So it depends on what you're controlling to determine exactly what kind of motor you want. These ones are pretty good, kind of like Swiss Army knives for servo motors. They're right in the middle. They can do a pretty good job at most of the tasks that we've tried them with. Now, how does the motor actually stop though? How does it go to 10 degrees or 50 degrees?
Or in those years?
Yeah, so the motor spins and then
At the stop, like the rapid signal, or no?
it has to stop. But how does it know where to stop?
So this is the position. I just added this one here. And these ones were lucky. They can actually turn more than, they can actually turn 300. Some of them have a top in here. So they're a little bit.
Well, if it wants to be able, if it needs to stop at 10 degrees, it has to know what the current degrees are, right?
But
So it needs to have some feedback
the motor
from the position of the output shaft to the electronic board here, to the controller, and the controller controls the motor as well. Right? There has to be some feedback, otherwise there's no way that the motor could turn and stop at the right time. So this feedback can be done in several different ways. You may have heard of encoders, motor encoders. Those are basically like your optical mouse. Before the optical mouse, there was a little wheel with little slots, and it would turn, and then the light would shine through, and you could count the number of pulses. That's an encoder. That one is very high accuracy. But the problem is it's only relative. It can only tell you if you're moving one direction or the other direction and how fast you're moving, but you don't know whether you're going at 10 degrees, whether you're currently at 10 degrees or 50 degrees. So then, with an encoder, you needed to have some kind of additional sensor that allows you to reset it so that you know where you're going. So then, that was done using end switches. So maybe you have a switch when the servo motor hits one end of its range, where it hits the plastic. Then there will be a little switch. Then you could record on that. Now you know you're at this position. Then you can move relative for a while, and there wouldn't be a problem. The problem is the end switches you usually needed the most when you turn on the globe, because when you turned on, you didn't know what position the glows were at. Right. After that, it worked reliably. But nowadays, this
So you need that many gears in order to get
not used anymore. The RC servos use an absolute position encoder, which is really just a potentiometer, which is a circular resistor. And then, as the motor turns, there is a little metal tab that moves along, and then you can measure the resistance of this resistor. That tells you then what the current position is. And this is also, this is pretty standard technology, it's still used a lot today. The more modern style is to use a magnetic encoder. So you put a little magnet on here, north-south, and then there's a chip that is sensitive to the magnetic field. Those are very nice to use. They are very precise, they are absolute, and they're very easy to mount. You can put them on the output shaft if you want to, if you have some kind of more complex mechanic. You can do that on the output shaft or inside of the servo motor. They use nowadays all magnetic encoders, what's called. So then we have this. Right? We have a resistor here, and our problem with the robot, building a robot like that, is we cannot use the motor directly. I cannot just connect the wheels to the motor because
when I cut this pin, this one is not going to turn. So the potentiometer will be stuck.
the motor spins about a couple of thousand times per minute. So your robot will be like a cruise missile. And there's no way that you'll be able to control it if you have enough torque. These small motors won't have enough torque to actually turn the wheel at that velocity. But even if you have more power and boom, the thing will be way too much. So we need to have the gearbox, which is why we want
it to be in the middle position.
RC servo. But we do need to keep turning
The motor
continuously.
backwards and forward. If I set it to one end, then
So-
it can only go forward. If it's at minus 90, then if I set it minus 92, it ignores it. So then I can only go to minus 80, so I can only go forward, but I have more range,
And then I
more
get more
speed,
motors from
range going forward, to control the velocity going
you can
forward.
start.
But I won't be able to go back. So the best thing will be to set it in the center position.
So what happens here is
Or
this controller board,
they have a physical stop.
we're implementing a controller to move that to a particular condition.
And then you have
That particular controller
this one now
in this
doesn't
case
have
is
one.
a PD controller.
Turn it to the center.
PID except no.
So we will have to program
zero.
the Raspberry Pi
So have you
to generate
have you guys worked with
1.5
PID?
millisecond PWM pulse.
You?
With that pulse,
No.
I'll be able to
Okay.
then set it to the center. And
Yeah. Okay.
So, the
More
hardware is
control.
pretty straightforward, and
We
it's
write
very
easy
easy
on
on
this
this
one.
one.
If you try and track the line, then I think it will become more
And then you have a continuous.
apparent. One of the interesting things is that people think this kind of problem, you could come up with an algorithm that should be pretty easy, right? Because let's say I'm currently at 10 degrees and I want to move to 100 degrees, then some kind of algorithm you could say, oh, okay, if I'm at 10, I want to go to 100, then I want to move plus. So I turn on the motor plus, then this one here will move, right? So it'll be 10, 11, 12, 13. Then I just wait until I'm at 100 and then I stop. Yeah.
Oh,
It's not quite that simple. Even a seemingly very simple control problem like that requires a little bit more thought. The reason is because when you wait until you're at 100 and then stop, then the motor is going to keep turning because of the
I'm sure you're not
it's going to stop at 105.
okay.
So then you say, now I'm at 105, but I want to go to 100, so I turn right. Then you turn the motor on, 105, 104, 103, 102, 101, 10. Now I stop. Oh, now I'm at 98. So your motor will never actually sit still at exactly 100. It will oscillate. And as we'll see in the afternoon, not only will it oscillate, but oscillate in a very bad way. So that's why there's this control loop in here, which
I mean, those.
tries to get the motor to that position. So what we want to do is for this motor to turn continuously and to be able to control the speed. So I want to be able to go forward fast and medium speed and slow speed forward and backward and backward, that kind of thing, right? And the way that we do that is, you gentlemen? Yeah. How do we get this motor to turn continuously?
That's forever. Then
I can't make it turn by going 1, 2, 3, 4, 5 degrees, setting it to that, right? Because it only has plus or minus 90 degrees for the range.
because I want to drive a robot.
No,
Otherwise,
no way to do that in software.
okay, with this one.
Well, keep going.
And then you can
Because
change
the
that.
control of this.
Yeah. And what do we disengage?
Years somehow.
Not the gears.
If this one has
Disengage the servo potentiometer. The measuring thing that says what position are you at.
go around in the loop, then that would work. But
And then we will set this to be the home position, 0 degrees. So then, if we tell the robot to move to 90 degrees, then it'll say, oh, I need to go to 90 degrees, I need to move very quickly. So it'll have a lot of
okay, good.
power to make the motor turn into that direction.
That's
But now this connection here is cut. So the motor will just continue turning, but the actual readback from the sensor is not going to change. So he's still going to reach 0 degrees. So they say, okay, more power, more power. Well, can you keep, which means the motor will spin quickly. If we go to 10 degrees, then it'll say, oh, I'm already at 0, so 10 degrees, I don't need so much power, I go slowly. So then it'll slowly. If you go to minus 10 degrees, it'll turn backwards. Right? So we're kind of using,
So you need to go to the
we're kind of cheating the PD loop.
okay. Then
So if you come to the front, then I can show.
but yeah, you need to install the Raspberry Pi Pico extensions. And then we can start a new project. We can start with an example and go with Blink. Go to W. I'm not sure where. No. Okay, so that should be a Pico 2. Okay, so then it should look something like this. Then you can create a Blink sample on your computer. Actually, let's do that. So after you install the extensions, then go to example and create an example. Equal to. Oh yeah, it's this extension. Yes. Once it is installed, then you can just click on it here. You will then have this one. This You will then have the Raspberry Pi Pico project, and then you should be able to you click on it, and you can say new C++ project. Sorry, new project from example. Then you can go Blink, Pico 2, do. And then here's the sequel. And then you can go to compile. And then that should work. And then let's see if I can run it. I have no data. Okay, then we flash it. So make sure that you can compile and you use it. And then we will control set the control for the okay. Yeah. Mhm. No, I think it's just downloading it. Depending on how good you make sure you're on the internet. And also, I think since you're here, check one thing. How much are those in Taiwan? What was it? They are 449 $1. Maybe we can buy some of those. They're a little bit more powerful. Oh, it's also quite expensive. This one here is 150. Oh, then let me change it so that I actually know my program is working. Here the delay is 250 milliseconds. So that should be twice per second then. 250 on, 250 off. Maybe 500. And I will set the timer. And that's just because I want to make sure. And in order to flash C++ program, um, you have to start the Pico in what's called boot selector mode, which is basically starting a bootloader. So there's a little white button. You just press the white button when you plug it in. And then no. Now it's like a second on, 1 second. I mean, you don't know. You can trust me. That's all it is. Yeah. Okay. Good. Did it download complete? Mine was. Yours is installed? No. Yeah. Really fast Wi-Fi. So that would be correct. But I don't know, do you have a USB? Never mind. I mean, this would work. If you guys no. But these machines are even on the wired network. Like, I don't know why they would be so slow. So let me do the next part then. We can start a new example then to have a look at how to control the servo motor. And that would be the other cool thing about the Pico 2 is that it actually has two different processors on board. So you can compile it either for the standard ARM core and also for the RISC-V core, which is the new one, the successor of MIPS. But the big thing about this RISC-V core is that it's actually open hardware, open source. So you can actually download the instruction set and flash it onto an FPGA, or there's companies building all kinds of processes like that. It's not competitive to the ARM with respect to power to processing power. So it requires more battery power than an ARM core, or at the same battery power, it's lower. But they're making nice progress with it. So I think it's nice to support that. Now we select examples. There's also an example on
We try.
yeah, but unfortunately you have to wait until. Is it finished now? It's rolling? Okay. Yeah.
Why?
Compile, and now before you plug it in, yes. You can also afterwards, if you know when it works, if you run, it automatically compiles. But now, for the first time, we just compile it first, so that all works. Then press the right button. When you plug it in, until you plug it in, then wait a second, or it should go ping. And now, I think we can let oh, that's correct. Yeah. Mm-hmm. Yeah, you can unplug. That's all there is to it. But if you have hardware, new hardware, getting the first lights to blink is a huge step of success. From there to having a humanoid robot is not that much further. If you can't get a button to blink, then you have trouble. So Okay, so I thought this was I actually wrote this. Yeah. So here's the SDK example for generating PWMs. Now, doing this on a computer, yeah, to generate this pulse, which means the pin is on, then off, then you wait 1.5 milliseconds, then you turn it on again, then you wait until 50 hertz, so 20 milliseconds, then the whole thing repeats. 20 milliseconds. That would be, how would you implement that? If you needed to do that on a computer. A loop, yeah. But what kind of loop would you write? Yeah, the timing is crucial, right? So this is really a real-time control problem here. So if you write something like for infinity, right? Forever, that pin true, that pin false. That pin false. Then here I need to do delay in milliseconds. 1.5. So we're doing it in integers. So let's say we have 16-bit, then I can do 1000. Or one byte, then I can do 150. And then set in true. And then delay until we have the 20 milliseconds here. So this would be my pulse. This would be pulse. 20 milliseconds. 200 minus pulse. Here's pulse. 15, 1.5 milliseconds. That will not work because if you run this on macOS or Windows or Linux, then your servo motor is going to oscillate, it's going to vibrate. And the reason for that is because all of those are not real-time systems. There's a lot of other processes going on. So if you open a web page, then this delay here will be delayed further. And then it will go off to one side. Sometimes it happens a little bit faster. So it's going to oscillate. The timing is not going to be accurate enough. So how do you do that then? If you were to do that on a CPU operating system, we actually only have the microcontroller here. So at least we don't open Firefox on the Pico. Right? But there's still other tasks that the CPU must do in order to maintain the operating system, even though it's a small operating system. So the timing wouldn't be okay, the OS is really not happy if you do this, right? That's the whole point. In the early days they used to allow that. So if you remember on the Macintosh, for example, I don't think any one of you remember, but on the Macintosh or on Windows machines, when you were formatting a disk, then the disk is spinning, right? At a certain speed. If you want to format the disk, you need to write the magnetic pulses onto that disk to store the data. And if you're too late, then the disk will have already spun by further, so the data will be useless. So that's why for the early Macintosh and the early Windows computers, when you were formatting the disk, everything shut down. You couldn't do anything until that disk was formatted. Like the mouse wouldn't move now. So there, the OS still allowed you to get a hold of the entire CPU, but modern OS couldn't do that. There are different styles of doing that. Basically, you need a very accurate timing source. And looking at the instructions here per computer, this is not accurate enough. So in Linux, you would set up a timer interrupt at a specific time. So you can say, okay, I want you to wake me up 50 milliseconds. That gives you much more accurate timing because that's independent of what else runs on the CPU. And the problem with that is it may still be delayed, but it's a lot more accurate. And the other thing is that while you do that way, you will have to incur the penalty of a context. So now the CPU is actually very busy, 50 times a second, which for desktop CPU nowadays is not a really big workload. But let's say you have something like a mobile phone, that will be like 20% processor load, just sending one PWM. Now, you want to control 30 motors for your humanoid robot, then you start to max out the entire CPU just setting pulses. So this is, however, a very common technique for controlling things. This pulse width idea is very robust. The reason why we don't just send like an analog voltage and say, oh, if it's 0 volt, then to the left. If it's 5 volt, go all the way to the right. If it's 2.5 volt and go somewhere between, then that's because that's very noisy. If you turn on the motor, the voltage will drop. If you stop the motor, the voltage will spike. So that's why we have this PWM, and it's very popular. So the Pico actually has 16 hardware channels inside that will generate this signal by you just sending the parameters. You say 20 millisecond delay, I want a pulse from 1.7 milliseconds. And then that will happen until you shut it down, without any work by your CPU. So that's what we need to set up in order to be able to control the servo mode. So here we have the code for doing that. Now these GPIOs, general purpose input-output pins, can be programmed to use the PWM function. So we set that up. We say that we want to use the PWM function. And then the Pico has like, I think, 4 different banks of PWMs that you can generate. So some of them can generate you can program it. So you can say like a couple of pins, I want you to generate at 50 Hertz. And and a couple of other ones I want to generate at 500 hertz. So you have like a different couple of bands, and then each band has a different channel. So that's at the very primitive level. And then I wrote a servo function here, which allows me to use the servo configuration. And then I don't need to deal with the PWM directly. I can set up which slice, which channel it uses, the clock that it uses, the divider that we use, and the minimum maximum pulse, and the frequency how often continue sending it, and then the current counts. So I generated 4 functions. Initialize the servo, just say that I want to use that servo, turn the servo off, which means make it available to the operating system again, and then either set the angle or set the speed for continuous revolution. Which really does the same thing, it just depends on if I have a continuous revolution servo connected or not. And then here's the implementation. So that particular pin I want to use the PWM function. Then here I figure out which slice that pin is connected to. Get the clock divider and the remainder. Then I set the PWM clock parameters. And I remember what I said here for pin and frequency and so on and so forth. Then I get the channel for the pin. And then I to turn it off, just set invalid servo pin in the configuration. I unset the channels to 0, and then here's the set servo angle. If it's a valid servo and the angle is less than 0 degrees, I clamp it between 0 and 180 degrees. Calculate the pulse width, set the correct parameters, and then set channel information. And this one is similar just for speed, minus 100. And as you can see, servo speed just calls that servo angle. So it just generates a speed relative to 90 degrees. If I say speed minus 100, then I want to go to minus 50. Or if it's too small a speed, then just turn on. Actually, this one, I don't know why. So this is just an extension of the VD code, and now I can Now, let's check which means that we use. Um, Actually, there's two ways to program the thing, but Pico, there's also a MicroPython implementation. But for something like this, it's better to use just straight C. So Oh, that one should be constant, because I don't want to change it. Config PWM const, that should be good. And maybe, I set the currency. Actually, um, and then um, So we want to power it with the USB battery. That's the other advantage of the servo motors. The max voltage is 6 volts, which means it's nice to USB. Oh, it's waiting for. It's waiting for 10. So we toggle it LED. The program is. Okay. Now my motor is running. You can probably have a look. So this just rotates through the speed. And even though we just the power from there, there's not that much difference in speed. But it's slow enough so you can actually control it and check for parts on the thing. And then that'll be done by the mobile phone. So let me just. Yeah, I think just needs to be a little bit more on the front. Plus, they need to get more friction on the tires. So the rubber band run. I had it moved there before, but and what did I want to do now? I wanted to um, rotating at about the center of the robot. No, we can try that, or you can try that. Is it hard? Not if you use the vision, right? Because then you can always correct for it. If you want to do this dead reckoning for an hour, then it will be hard. Very likely that. No, I wanted to see what's the other. That should be. So now we need two configs. Two. And this is not 16, but this is 28. And now the angle, if this code is actually wrong, you can tell me why. First of all, it's wrong because this should be servo 2, of course. But, wrong in a more interesting way. Which you get often in robotics like this. You only to go forward, but since the two wheels are, one is right, one is left, they are rotating in the other direction, so it's now spinning on the spot. Actually, this turns pretty well on this spot. So the velocity is pretty good, actually. But if I wanted to go forward, then of course one has to spin right, the other one is left. This is always very annoying. So let me just fix But now the problem is this will be angle 90, angle of minus 90. Angle of minus 90. That's positive. I want to subtract it. So 90.0 f minus angle minus 90. That would be the same as minus angle. Because my 0 point is 0 degrees. And 90 degrees. 90 degrees will be the. Oh, that's what I wrote. That's why I wrote the speed function. Now I know what I wrote. Because that's ended at 0. Then. The other good thing to do, by the way, is when you program your robot, A, keep it low to the ground so it doesn't just shoot off, and B, give it a couple of seconds before it actually starts running so that you can make sure you actually want it to move now. Too many times I've seen robotics people that flash their program onto the robot all excited, then the robot takes off, falls off the table, and it's broken. Ah! So, as you can see, it's not that accurate. There's a little bit of a bias, but at least it's kind of consistent. It's straight enough. Right? With the vision system, you will be able to correct for it. And so we'll compete against the German guys with their turbobots. We have some more servos, so you can still have a little bit of time. I'll set this one to 0, both of those, and then we can flip the pin, and we can do that for some other servos, and we can build 3 or 4 of these. And I actually have this one here, where you can mount a mobile phone. This can be the cover on top of the robot. And then I actually think it looks a little bit like the Dalek from Doctor Who. They can go, exterminate, exterminate, because they always try and kill all the humans. You guys know the Daleks? No. want to change the code now to just be set at 90 degrees. So I'll just comment this line out, which means speed won't be changed. Speed will stay at 0. That should be the center of. And right, do we have a shot? Sometimes they have a mark on the horn to show you where 0 degrees is, but these ones are for $3. They're not going to put some guy there telling you exactly where it is. So we're looking at in and control is the speed is 0, it turns off. So here, I want to yeah. So this is at 0 now. Not using the I'll move the one. Just the other one. Okay, we'll use the guidance of, but then our Oh, and also, no, it's not this one. This one came from here. There's another one. But that's the difference. Yeah. No, that's the second one. I just okay, we'll put this one together. There it is. Yeah. I just wanted to say maybe it's in the top. That was also a pretty good magic trick you did there. First you make the pin disappear and then you reappear. So today then for the class, the German students, we'll just bring you up, match you up with one of the things here. And Very simple. Correct. Mhm. Okay, then Ray, get a Sharpie so we can label those. Like a black or white marker. Because we need to write down the use. Otherwise, somebody's going to build a pen out of this. Oh, come on, control this one.
I don't think I'll be able to contact.
No, you mean in afternoon?
Yeah.
Yeah. I will post the link in the Discord channel. Actually, what's your ID? And I can give it to it will be a big blue button thing. Have you used that before?
Yeah.
Really? I didn't think. I guess it's popular in Europe.
Yeah.
No, those. Maybe. Maybe. Report. Uh, the magic trick. Yeah, part of it is completely. The detective part is very different from. Mhm. Yeah. We just need to mark it. Otherwise, I know for sure. Like the Sharpie there, because the image can be peeled off.
Okay.
And yeah, if you cannot use the Sharpie, you can use the label.
I believe we have.